All right, we've got a question here that gives us the circumference of a sphere to be measured to be 84 centimeters with a possible error of 0.5 centimeters, and we want to use differentials to estimate maximum error in the calculated surface area. What is the relative area? And then for part B, we want to use the same differential to estimate maximum area and calculating the volume. And then what is the relative area? Okay, so to start off, we want to first write out our circumference equation. Just 2 pi r. We know that's equal to 84. So we can calculate our radius be equal to 84 over 2 pi. And that'll be equal to 42 over pi. All right, now we want to differentiate both sides. So we'll get the differential of the circumference is equal to 2 pi dr. And essentially, we're taking the differential of this equation. So we can create an equation that gives us the change of the circumference with respect to the change of area. Excuse me, with respect to the change of radius. Okay, now we know that our change in radius, we're told that the possible area is, we're told possible change in circumference is 0.5, right? That's the amount of error we have. So we can then use that to calculate dr and say, well, then dr is equal to 0.5 over 2 pi. And that'll be the same thing as 1/4 pi. All right, now, if we use the equation for the surface area of a sphere, we know that's the same thing as S equals to 4 pi r squared. All right. Now, if we did the same thing here, where we took the differential of the sphere, we can calculate the change in the change in surface area of the sphere with respect to the change in a radius. Okay, we have 8 pi r dr. All right, now if we go ahead and plug in the values for r and dr, number one, we know that our r was 42 pi, we calculated that to be. We know our dr, we calculated it to be 1/4 pi. So we can calculate our ds to be 84 pi. Excuse me, I'm sorry, it should be 1/4 over pi. 1/4 over pi, and therefore this would be 84 over pi. And we're told that everything is in centimeters, so we'll have centimeters squared. And then when you actually go ahead and divide this out, it comes out to be approximately 27 centimeters squared. Okay, 84 divided by pi. All right, now if we want to find relative error, we would asked to use, excuse me, let me just reread this question. We want to use the differentials to estimate maximum error in the calculated surface area. What is the relative area? Okay, so our maximum error is here. Okay, and then if we wanted to calculate our relative error, we could use the equation. The change in S over S is approximately the same thing as the change in S, d of S over S, right? So delta S over S can be the same thing, the same ratio approximately as the d of s over s. And we know d of s over s is the same thing as 8 pi r dr over s, which we know is 4 pi r squared, right? Our s here is the surface area equation, and our d of s is the derivative of it. Okay, when we go ahead and divide these out, we'll be left with a 2. These would cancel out. This goes to a 2, and then 1 r in the bottom. So 2 over r, and we have a dr. Okay, if we go and substitute our r and dr values, we know that our dr we said was, what did we say our dr was? 1 over 4 pi. Yeah, we said our r was 42 over pi. Okay, if we go ahead and divide all that out, it'll come out to approximately 1 over 84. And if you convert that into decimal, it is approximately 0.012. And we can also write that as 1.2% error. Okay, so we can see here that if there is a possible area of 0.5 centimeters in the circumference of the sphere, then the relative area error for the area, the surface area, would be 1.2%. All right, now for part B of this question, we're asked to use differentials to estimate the maximum error in the calculated volume, and then what is the relative error. Okay, so we're going to use a similar approach. We're going to write out our volume equation, which we know is 4 over 3 pi r cubed for the sphere. And if you take the derivative of that, you'll get 4 pi r squared dr. Okay, here we know our r squared, our r was 42 over pi, and our dr was 1 over 4 pi. If we plug all that in, 42 over pi, and then we have a 1 over 4 pi. And if we go ahead and expand all that out, it comes out to be approximately 179, and this is all in centimeters, and volume is cubed, so we have centimeters cubed. Okay, and then once again, we can use the same. This would be our maximum error, by the way, for volume. And then we want to use our the similar approach that we did last time, where we said the change in, the delta V over V is approximately the same thing as dV over V. Sorry, dV over V. And that would be then the equation, which is 4 pi r squared dr over the volume equation, which we know is 4 over 3 pi r cubed. And then all that simplified out comes out to be 3 dr over r, excuse me. All right, now if we go and plug in 3 dr equation, if we plug in dr, which we know is 1 over 4 pi, and then we plug in our r, which we calculated to be 42 over pi, then we would have all of this approximately come out to be 1 over 56, which is roughly 0.18. And we can write that also as 18%. I'm sorry, 0.18 would be 1, 2, yeah. I'm sorry, I did this wrong. This should be 0.018. Okay. And then we would have a 1.8%. All right, well, I hope that clarifies the question. First, what we did is we used our circumference equation to calculate for d of r and our r, and then we used the relationships between delta s and delta of the surface area over surface area and d of s over surface area to calculate the maximum error, and then we were able to get the relative error in percentage, and we did the same thing for our volume. All right, well, I hope this clarifies the question, and thank you so much for watching.